Good morning, everyone. And first of all, thank you to the conference organizers for extending an invitation to this event. I'm going to provide you a little bit of review of some of the research that I did over roughly a 20-year period that has led to the developments that you'll see here that primarily relate to figuring out a way of measuring the impact of odors on communities. So I'm particularly interested in this aspect of dimensions of odor impact, but based on specifically the odor's characteristics. Probably this slide is a bit of a waste of time for many of you because I think you know there is a major problem associated with odors. First of all, they're ranked as the major generators of public complaint in communities. Primarily, we've got evidence in North America and Europe, but I suspect the same is around much of the world. And odors, while many people perceive them simply as a nuisance, in fact, there is very important effects in terms of physiological and psychological health. And so therefore, these things, the odors need to be dealt with in a very proactive way. Industries, I would argue, and regulatory agencies, however, currently lack an effective and objective basis for assessing the impacts of odors on communities. Even though there are many, many different types of methods out there, I think one of the things that a lot of consultants in particular find is that technically they're very, very challenging, sometimes very, very expensive studies to conduct. So we really need a simple and effective approach. And I would argue then the lack of effective methods actually leads to a situation where we're actually hindered from preventing odor impacts before they occur. So the overall motivation for the kind of work that I've been doing for a very, very long period of time, since I think I did my first study in this area in about 1980, in that time I've been sticking to one issue. That is, an effective method is required to assess the impacts of odorous emissions on communities in order to prevent, minimize, or eliminate community odor nuisances. I would argue that an ideal assessment method should have a number of things in place. One, it should be logical and simple to implement. It should be based on quantifiable variables, and in particular, I like the variables summarized as FIDAL, that is frequency, intensity, duration, offensiveness, and location. And it should provide a means for predicting potential odor impact before it is actually created. Now, most of you, or a lot of you, probably conduct a lot of work using simply the dilution to threshold principle. So the idea here is that an odor can be characterized, and it's a pretty interesting measure. An odor can be characterized by the number of dilutions that you must subject the odor to in order to reduce it to the point where only 50% of your population respond to that odor. Measurements of prediction odor concentration then can be done at sensitive receptors. So if you're particularly worried about an impact on a community, a home, a park, whatever it may be, you can do either field measurements of this sort or you can try dispersion modeling to predict the concentrations. And then ultimately you can compare them against some sort of norm. I think this is the most common approach that's in place throughout the world. So the overall approach, this is just an example of a study that I did. It was actually a 2-year study where there was a long-standing odor complaints for about a 30-year period prior to that time, where we did a whole series of investigations in the field and in the processes themselves within this factory to determine under what kind of conditions there were impacts noted in a neighborhood. So in this simple case, what we did is community surveys, walking around with a team of odor panelists that was changed over the course of a couple of years. They would register their response in the field to the odors, and we would correlate that with processes ongoing in the facility. And then through dispersion modeling, what we could do is predict under certain weather conditions what were expected to be the number of odor units in the community, and thereby be able to correlate our modeling results with our field investigations. And I have to say, overall, we were quite impressed with the number of field investigations over 2 years, where the dispersion modeling process we put in place did seem to have a very good correlation with the impact in the neighborhood. But I would argue that there are very severe limitations associated with the dilution to threshold principle. So first of all, I would argue that odor concentrations at selective sensitive receptors, which is usually what we either model or where we do our field measurements, really don't reflect the overall population impact, that is the community impact of the odor as it is dispersed over the community. I would also argue that thresholds don't account for the highly variable sensitivities of individuals within a population of odors. Very too often, I found a lot of people who are in the area of the odor investigations lose sight of what an odor threshold is. It is the point at which 50% of your people respond to an odor. The implication, of course, is that there are 50% of the people who do respond and 50 who don't. So if you go below that odor, some people think that as soon as you go below the odor threshold, the odor is gone, it's no longer an issue. But in fact, I could show you many, many case studies where we did with our populations, our panelists, where if you dilute the odor fivefold below the odor threshold, roughly 10% of your population is experiencing the odor. In other words, when you're at 1 odor unit, those people are experiencing 5 odor units at a personal level, so 5 times their personal threshold, which means that the odor threshold by itself doesn't capture the full dimension of the potential population impact of that odor. I would also argue, and it's been thought about for many, many years, that odor hedonics, that is, its character, its offensiveness, are not considered in this approach, and therefore we need to be able to distinguish between odors that maybe arise from a bakery versus those that might arise from an asphalt facility. Though I should note as well that a bakery odor, if a bakery is fired up early in the morning and you open up your windows 7 o'clock in the morning in the summer and you smell baking bread coming over you day after day, that can actually itself become quite annoying. So you need to account for that sort of thing. Actually, the most difficult cases that I've dealt with, 2 of the most difficult cases, one was with a Kentucky Fried Chicken outlet, which when you drive by it on say 5 o'clock in the afternoon heading home, you think, I could stop and get some chicken. If you're cooking that chicken at 7 o'clock in the morning and you have the smell of those greasy frying going on, it's a whole different story. So the overall objectives of the work that I've been doing are as follows. 1, to characterize odors over the full range of conditions under which they can be experienced. Then to develop, test, and implement methods for predicting and quantifying the effects of odorous emissions on the entire community population. I want to take into account the odor characteristics, including local meteorology and geography, land use patterns, and population characteristics of the community. And then to develop simple, inexpensive, and flexible software to actually assist in the conduct of impact assessments. That's a pretty tall order. I can't say they've achieved all those objectives perfectly, but we've made, I think, some pretty good headway toward that. The fundamental basis of this is what we call an odor impact model. Some of the original work that we published in this area probably came out in 1981, 1982, somewhere along there, and we've been applying it in various fashions over the course of the years. So in this case, what we do is we actually conduct measurements where we use a modified force choice method in conjunction with a dynamic dilution olfactometer, which is a pretty standard procedure. But rather than just looking for the threshold, what we're actually doing is gauging the response of our panelists to that odor over a whole range of concentrations. So in effect, what we're developing are dose-response relationships. So these are established in terms of both the probability of response and degree of annoyance. There are many, many different ways of doing either of those, but I'll just note here, I've got detection and discrimination here. Detection is the terminology I use it for is a typical force choice method where you require panelists to pick one of, say, 3 ports that is emitting an odor, and based on their positive identification, they are construed to have having detected the odor. Discrimination is an added level beyond that, where we actually say not only tell us which of the ports is emitting the odor, but tell us the degree of certainty that you have associated with that. And I actually firmly believe that discrimination is a much better measure of thresholds than, or indicator than detection. And the degree of annoyance, as I'll show you, is an indication of, it's a way of just gauging the response of those individuals. So coming back to the idea of odors having multiple dimensions. This is the single dimension that you measure under the dilution to threshold principle. So the idea here is that at 50%, you have a certain number of dilutions of the odor at which that population can detect the odor. So all your work goes to find this single data point. And then people go off and use their dispersion modeling, etc. I would argue there's a lot more to this, though. So particularly if you measure a dose response curve, as you start at a low number of dilutions and proceed to a high number of dilutions, you go from 100% response or positive detection of the odor down to 0. And going back to this case again, so you can see in this case where at one particular concentration 50% detect the odor, if you go out much further here, maybe in this case about 3-fold a higher number of dilutions, you still have roughly 10% in this particular instance of the population detecting the odor. And of course there's other people with odor personal thresholds that are on the other side as well. So this represents a cumulative distribution or probability distribution of the odor thresholds within your community. I would also argue that people will register different levels of annoyance. And so the idea here is that probably at 50%, right here roughly at 1 odor unit equivalent, you'd see there's a very small response or annoyance. But remember, there's a fraction of people who are detecting the odor much higher than their personal thresholds. They do register a degree of annoyance, and so that degree of annoyance causes it here. But of course, as you go to much higher concentrations beyond that, you end up with higher and higher degrees of annoyance. And on this scale of 0 to 10, eventually this will make its way up to a high of 10. But this doesn't tell the whole picture, because you can see in many, many different samples that we've seen out there that the shape of the profiles also have very different characteristics. So for example, here, all these odors, A, B, and C, all have the same number of odor units in any given sample. But there's a very different curve here. The idea here is something that we're terming persistence. The persistence of an odor is a measure of how persistent the odor is as you dilute it more and more, let's say beyond the threshold. So the idea here behind A is, notice that as soon as you dilute it beyond the threshold in this area, the population response plunges. So that's not a very persistent odor. It's an odor that if you just push it a little bit further beyond the odor threshold, the number of people in the population who detect that odor or respond to it drops precipitously. But there are other odors where they're very long. One of the most persistent odors that I've ever discovered is cigarette smoke. It's amazing when you put cigarette smoke through an olfactometer, just how far you can dilute it, and people still detected a significant amount of that odor. So in this particular case, for this odor C, as you really, really dilute this out, you still have a very significant fraction of the population still responding to the odor. And so all this for the same odor threshold, for the same number of odor units. Then likewise, you could argue that there are different hedonic curves here, different annoyance curves that would happen. So again, think about that bakery odor versus an asphalt facility, where you might have something that drops precipitously but is very annoying. So in this case, you have a very annoying odor, but as you dilute it, the annoyance drops off very, very quickly. And this other one, C, it's maybe less annoying initially here, but it still persists even through a whole range of dilutions, thereby causing perhaps more impact beyond conditions that you might otherwise expect. I would spend a lot of time, and I derived over the course of it took a lot of work to figure this out, but we produced an equation that models this type of behavior actually quite well. It's simply this equation. It looks more impressive than it really is. It's not really that impressive. It's just simply a modified logistic equation. Probability of response is a function of the threshold, D50. So this is something that most of you would already measure in your work. So probability of response is a function of dilutions, and there's two parameters. One is the number of dilutions required to reduce it to the sensory threshold level, and this other term n appearing in this exponent, which I purposely configured to have possible values between 0 and 1. This n is a measure of the persistence of an odor. So this is a model that shows you for an odor which has a certain number of a certain odor threshold here. Different odors have different characteristics curves, where if n is equal to 0.1, you have this catastrophic drop-off. So in other words, you have a very, very low persistence. And this one here, n.9, is something that's an incredibly persistent odor, so that even as you push it way beyond the dilutions expected to bring it to the threshold, you still have a significant fraction of your people responding to the odor. So that's a very simple two-parameter equation that we could use to relate the odor concentration to the probability of response. This, by the way, if you just take the derivative of that nice-looking equation, it actually gives you the probability density function. This is essentially what is the distribution of the odor thresholds within your community. So depending on the persistence, you end up with different characteristics of these curves. And I'll show you an application of these curves in a moment. Degree of annoyance is another issue. There's many, many different ways that you can get people to respond to the odors, and I'm not suggesting that this is the best of all possible ways, but a number of you, if you've ever been in the hospital and you're reporting a problem, and the doctor or the nurse will ask you, on a scale of 0 to 10, how does this pain register? I never know how to answer that question, right? What is 10? You say, oh, it's the worst ever. Well, paper cut, that's bad, but I'm having a heart attack. I don't want to underestimate the pain there. So what you have to do is give people some sort of normalized way of actually saying how bad they are responding to the odor. And so what we created is originally a 0 to 10 scale, found that wasn't producing very reproducible results. Then we threw a couple of normative statements here, descriptors, tolerable, unpleasant, very unpleasant, terrible, and unbearable. But those are very difficult even for you to register against. You can get some degree of understanding of what you're trying to achieve. We have much more complex normative statements that we've used as well, but I would actually argue that the most effective methodology has been just using a little graphic, where people actually can relate their personal emotions to that of a figure, and they say, I can relate to this character better, and this produced a dramatic improvement in the reproducibility of the responses of the individuals. So on that basis, what we did is we measure out the annoyance at a whole range of different odor concentrations, and it turns out you produce the same sigmoid curve that we saw in the other case. And so this lent to the possibility of using the very same type of equation, a logistic equation here, where annoyance is a function of dilutions of the odor with two parameters. D5AU, 5 AUs is 5 annoyance units. So this is essentially the dilutions at which you have 5 annoyance units being registered. And A is essentially a persistence of annoyance. There's some odors that as you dilute them, they become less and less annoying, or conversely, as you concentrate them, they get more and more annoying very, very quickly. And other odors have a different characteristic. And then we actually, I looked at this and said, wait a minute, we should be able to modify this equation. So I created this thing called the response ratio. This response ratio is simply the number of dilutions at which you have the odor reduced to 1 odor unit, and this is the number of dilutions at which you have 5 annoyance units, and the two of those is a dimensionless parameter, which I call the response ratio. If you just push this into that equation, you have annoyance as a function of dilutions, and your parameters are the response ratio, the odor units, or the D50, and then this other thing, which is the persistence of annoyance. So these we've applied to a number of different chemical species and odorous samples and shown that the curves work remarkably well for a whole range of different kinds of conditions. So this is just an example of something that I published a number of years ago in an atmospheric environment paper where we characterized different types of chemicals and showed the overall process. And by the way, when we fit the curve to these results, and then we calculate the odor threshold according to the methodologies that most people produce. It produces almost identical values. So the curve fitting process that gives you the persistence in the odor threshold produces the same threshold as you got through, let's say, doing a geometric mean of a large number of individual panelist thresholds. That probability distribution curve that I showed you earlier, one of the things we're always interested in is optimizing the design of our approach for measuring these kind of effects. And so there's a whole bunch of different ways that you can design your apparatus or your experiment to expose your panelists to the odors. And one thing I've often found is quite annoying that you have to build an entire system and then run the study to determine the reproducibility. The great thing about having this probability distribution is you can model your apparatus before you actually build it. So this is an example of experimental data we did on an existing system where we knew the threshold and we knew the persistence of the odor, and we took different panel sizes ranging from 1 person all the way up to 25, and actually went a lot higher than this. And then we measured the variability in the threshold between different panels. And then we did it as a pure simulation from the equations. And you can see the experimental and the simulation are incredibly well matched here. So again, that shows the utility that if you know these characteristics of your population, you can actually use those characteristics in the design of your study before you actually build it and execute it. So the application to impact assessment is as follows. You then extract your thresholds and your best fit parameters of the persistence N, this persistence of response, A, which is a persistence of annoyance, and this response ratio from the curves of the odor impact model. You then use dispersion modeling to predict spatial and temporal variations in odor concentration, probability response, and degree of annoyance using these equations. So that ratio D over D50 is an example. D is the number of dilutions. D50 is the number of dilutions required to reduce it to the odor threshold. And so the ratio is actually equal to the odor concentration in odor units. So the simple equations are as follows. This probability is a function of odor concentration, and this parameter N, the persistence. This annoyance is a function of C, odor concentration again, R, response ratio, and A, which is the persistence of annoyance. And then the idea is to use this capability to then evaluate parameters that can help you determine community odor impact. So going back to that field study, so we had this original approach, which was just to develop the contours of odor concentration, field studies to verify that it's actually matching, the modeling is actually matching what we're noticing in the field. And then using those functions, we can then map the odor concentrations onto probability response curves and annoyance curves out into the community. Well, this is just the first step then. So what do you do with it? So then you have different means of actually measuring odor impact. And I have argued in one of my papers that there's probably an infinite number of ways of doing this, but I've identified them in one-dimensional, two-dimensional, and three-dimensional parameters. One-dimensional parameters are, say, peak concentration, probability response, or annoyance at selected sensitive receptors, or if you want, at the most impacted receptor in your community. So you can look for specific impacts at specific locations, or you can look for the most impacted individual location. 2D parameters broaden it somewhat. So the idea behind a 2D parameter is if, let's say, you're 50% contour. So this is a geographical area. Here's the probability of response curves, so known as a 3D graph. This contour here is an example of a footprint. So if you wish to calculate the community response, you can do it based on the size of the footprint of the odor in that community itself. So if you want to use the 50% contour, you can use that as a footprint, 10%, and on. 3D parameters, however, recognize that within an individual location here, the impact can be considerably different. So you can weight that according to either by concentration, by probability, or annoyance. So, or you can actually determine the population within a given contour to give an estimate of that population. And this is my favorite, the number of persons responding. If at any location you know what the odor concentration is, you have a probability response equation. If you know the population density of that location, you actually know the number of people in that location that should be able to respond to the odor. Integrating under this curve gives you the total number of people who are likely or able to respond to the odor under any given condition. An example of this is shown here for a study that we did where we have a series of these odor impact models. There's no annoyance on these. It would just, here's a series of conditions where we looked at the single peak hours that occurred over 5 years, all 1 hour peaks over 5 years, and then the 99th percentile of 1 hour peaks over a 5-year period. And from these, we end up with different footprints. In our particular case, we had a particular receptor here where in this first condition here, it looks like, oh, the peak doesn't hit anywhere near receptor A, but that doesn't matter. Under some other conditions, receptor A is in a dominant footprint associated with this odor. And then even looking at the 99th percentile of 1 hour peaks, some people say 99th percentile, that's pretty rare. 99th percentile is not very rare. That's roughly 3.5 days over the course of an entire year. That's a lot of time to be bothered by an odor in your area from year to year. Using that information, and then with a population density map, and by the way, the population density map can help you, that industrial facility that we did that one big study on for a couple of years was right adjacent to a lake. There's no population hanging out on a lake except for occasional boaters here. So you should exclude that from perhaps some of your population or footprint calculations. So on this basis, we can calculate all these different receptors. I won't cover all these impact parameters, but just looking at this case here, under peak condition, if we map out what happens, what's the number of people that will respond to the odor under the peak conditions that would occur at every individual receptor, in that neighborhood or in that community, it was 9,070 people. That's not an insignificant impact. Or say the 99th percentile here. So 99th percentile mean that 2,010 people are bothered 1% of the time, or are responding to the odor 1% of the time over the course of the year, which again is almost 4 days out of the year, which is not insignificant. This kind of argument makes a whole lot of sense when you stand in front of a court and you say, this is the kind of impact that is being endured by this facility, and this is why these neighbors of this area are actually have a right to be concerned about what they're experiencing. You can also play with the effects of if you want, various types of approaches that you can use to mitigate the odors. So this is an example of the base case where we had 100% emission rate, the current emission rate, with a persistence of 0.3. And notice here that if you were to modify the odor, keeping the same threshold, but modifying the persistence, looks what happens to the number of people who are responding to the odor. 2010 drops to 1,350 in the case of a reduction just by 0.1 units of persistence, a major increase. So this to 2,980. This explains a lot of the studies that I did where people used some burning devices to oxidize some of the VOCs, and they measured a decrease in the odor threshold, but in fact what they seem to have done is they've increased the persistence of the odor. So where they thought they were putting an odor control technology that would be effective, it actually had the worst effect. It actually created a more persistent odor even with a lower level of odor threshold. And you can do the same thing in terms of modeling, in this case, reductions in the emission rate. In this case, we kept the persistence constant. And you notice here, if we managed to drive the odor emission rate down to 10%, we're down to 26 people that should be impacted by the odor under that condition. So the idea here is to make your lives easy. I had graduate students working with me. Graduate students spend a lot of time at very low rates of pay to carry out their work. It's not something you may not have the luxury of doing. That's not kind of thing that you want to do on a regular basis. So the idea was to develop post-processing software to actually do this for you. Implemented everything in Excel to avoid a whole lot of hours of work. This Excel tool is simply you just input from your dispersion model into the sheet an input concentration in odor units, the population density, and then you input the other characteristics of the odor. And then it calculates automatically what the probability of response and annoyance would be across various areas, allowing you to map out these footprints in very interesting ways. From there, you just have a simple input interface where if you want to calculate, as an example, a footprint, inside the one odor unit contour, it tells you how many square meters are encompassing that, and all kinds of population inside contours, population weighted responses, and then footprints that we can calculate. So it's a very simple thing that we developed over the course of a couple of days to just take all of this work and make it very simple. So the idea is then that you could explore control options for your odors. You can do the pilot studies to actually measure what are the characteristics of the odor. You can conduct the dispersion modeling. You can do the evaluation of these parameters that I'm suggesting in this simple analysis. From there, you may have to go back to explore other control options. Eventually, you come back with a satisfactory solution, and you've got the implementation phase and the follow-up in your community. So there's a lot of things that we did here. I'll be happy to talk to you about them over the coming days. But essentially what we did is we think we came up with a relatively simple approach overall to assessing community response to odors, and thereby provide you with a basis for actually both analyzing the current situation and predicting where you're going to go with your control options. And I have lots of papers to share with you if you're interested in reading this even more. Thank you very much for this morning for your attention.
Thank you, Jane, for this very interesting presentation. Do you have any questions for Jane for about 5 minutes? And we will be here, so we will be able to discuss a bit further after, but we have any questions?
Thank you, Jim.
You're welcome.
I wanted to see how, during olfactometrics, how do you determine those R and, R I got, but how do you determine the annoyance persistent? Do you run your olfactometer over many panels? Or?
Yeah, so the idea here is you select a panel of individuals. Unlike many other types of odor studies where you might test your population to reduce your number of people to have odor thresholds within a narrow band so that you end up with a highly reproducible series of odor thresholds, there is value to doing that, but not for when assessing odor population. So you have to take a random distribution of people from your population. Now I did quite a number of studies, and in fact you can see the way I use the probability distribution curves to show how as you sample from your population, you end up still always with some variability between panels. I found that as soon as you hit about 30 people, you've got a sufficient representation of your population, and you'll be able to get good numbers out of that overall.
Thank you so much. You have another question?
Can you identify some of the population that you have been tested are sensitized or a particular chemical?
Well, in our case, we actually choose not to do the sensitization approach. So I know some people take their population that they're from the local population is impacted by the odor. And again, there's value in doing that because then you can test the response of those individuals to the odor. In this particular case, I would always tend to take people away from the impacted area so that we don't have to deal with sensitization issues. What I don't mean to claim here is that this captures all of the responses of all the population at all, because there will be sensitive and hypersensitive individuals. Particularly, I know there was a couple of people that I dealt with that over time became incredibly adept at identifying the presence of the odor at incredibly, incredibly low levels. And so they developed their own sensitization. I tried to avoid that. And I would argue, when it comes to a regulatory framework for dealing with individuals like that, this is not the approach that you're going to deal with them. Then you have to get into some other dimensions, the nuisance provisions of common law, et cetera, that have to be utilized to satisfy their needs.
Any final question?
Did you do any work on combination of different odors?
Yeah.
Because I saw your persistence was for individual compounds, but once you start mixing, what happens to that?
If I had done that, I'd have the Nobel Prize. So we did some work where we did add, and in fact, a number of the chemicals that I showed the curves for there the additive effects were pretty clear overall, that you could actually correlate them. But those odors were all nice, pure odor and chemicals of a certain organic, or a certain structure, chemical structure. So it's not surprising that they added up well. I think what happens is, just by virtue of the fact that you see these different persistences, it tells you just how complicated this is. You just cannot do that whatsoever. So one thing I was playing with for a little bit was to see that, okay, if you can model out what is the fraction of people that respond to individual odors at a location, could you in some way combine the probability of individual responses together to get an overall response to a mixture? I haven't figured that out yet. I've done a lot of math to try to figure out ways of doing that, and I'm still not convinced that it's doable at this point. If you have ideas, let me know. We'll share the prize.
Okay, thank you, Jim, again for this presentation.